Hello students, welcome to the class. Our next question is from the kinetic theory of gases. Right? Already synopsis and few questions are completed. Next, let us discuss the next question. The question number 29. The equation of state corresponding to 8 gram of O2 is. So here they have asked the equation of 8 gram of O2 molecule. Right. So how to write the solution? That is, as we know that as we know that 32 gram of O2, it means it is 1 mole. It is 1 mole. Right. Therefore, 8 gram of O2 means, therefore 8 gram of O2 means, can we write it as 1/4 mole? Right. So for 32 gram of O2, it means 1 mole here. Therefore, for 8 gram of O2, we can write it as 1/4 mole. That is nothing but, so that is mu is equal to 1 divided by 4. That is nothing but the number of moles is equal to how much it is now? It is 1 divided by 4. So what is our equation? Our equation is PV is equal to mu into RT. PV is equal to mu into RT. Therefore, we will get it as PV is equal to 1 divided by 4 R into T. Or we can also write it as RT divided by 4. RT divided by 4. See the options. They have given the equation 1. That is option A. PV is equal to 8 RT. Option B. PV is equal to RT by 4. Option C. PV is equal to RT. And option D. PV is equal to RT by 2. Here the correct option is option B. That is PV is equal to RT divided by 4. Right? Next question. The expansion of an ideal gas of mass M at a constant pressure P is given by the straight line D. So you can see in the figure, we have the graph of volume versus temperature. So different ideal gas they have taken A, B, C, D, E. Right, the corresponding value of volume is given like 1, 2, 4, 6, 8. See, question is what? The expansion of ideal gas of mass M at a constant pressure is given by the straight line D here. Is given by the straight line D. Then the expansion of the same ideal gas of mass 2m at a pressure of P by 2 is given by the straight line. So here in the given graph, D represents the expansion of ideal gas of mass M at constant pressure P. They have asked you, when the mass becomes 2m and the pressure becomes P by 2, which straight line represents the respective condition? See here, that is according to ideal gas, we have that is PV is proportional to M into T. PV is proportional to M into T, which implies we can also write it as V is proportional to M divided by P into T. Right, M divided by P into T here. So what is this M divided by P? This M divided by P, it represents the slope of this given straight line. It will represent the slope of this, whatever the graph is given. So in the first condition, what they have said, this m by p represents the line d. M by p represents the line d here. So next condition, what they are specifying, when the mass is doubled and the temperature pressure becomes p by 2. So if I simplify this one, what it happens? 2 will go to the numerator, it becomes 4 into m divided by p. Okay, which means that m by p is what? M by p is your slope. So now the slope is becoming 4 times. The slope is becoming 4 times. So slope is becoming 4 times means for d, it is m by p. So 4 times of d, that is nothing but what? Here you can see that is d is here 1, 2, 3, 4. That is a is having the value of 8. 4 times means what happens here? That is 8. That is nothing but option B. Option B is the right option, which means that when the mass becomes 2m and the pressure becomes P by 2, the straight line is represented by A here. The straight line is represented by A. Suppose if they give any other condition like mass becomes 3 times, pressure becomes 4 times, something like that. Again, you can substitute here, simplify and see which line it is representing. Here m by p is nothing but slope of the given straight line. Okay. Next question. A gas is container. In a container A is in thermal equilibrium with another gas in container B. Both contain equal masses of the two gases in the respective containers. Which of the following can be true? So what they have said, in a container A is in thermal equilibrium with another gas container B. Okay, both have the equal masses. Then which of the following condition is true? So we can verify this one. That is, see here, according to this problem, what we can write? The mass of a gas are equal. As the mass of the gas is given as equal, the number of moles will not be equal. So when they said, sorry, when they said mass of the gas is equal, then we can write it as mu A is not equal to mu B. Mu A is not equal to mu B. So for ideal gas equation, it is given by PV is equal to mu R into T. Right. The next, for two gases, we can write it as PA VA divided by mu into A is equal to PB VB is equal to mu V. As the temperature of the container is equal, that term will get cancelled, and the R is also the universal gas constant, that term will also get cancelled. So from this relation, what we can see? We can see that PA is equal to PB and VA divided by VB is equal to, we can write it as mu A divided by mu B. But this is not equal to 1. This is not equal to 1. So when it is not equal to 1, what we can say? VA is not equal to VB. We can say VA is not equal to VB. Right? So this is what, when PA is equal to PB, we will get it as VA is not equal to VB. But if I take it as, similarly, we can do in another way also. Suppose if you consider VA is equal to VB, that time here what happens? VA is not equal to PB. PA is not equal to PB here. So you can see the given option. First option is given as PA VA is equal to PB VB, right? So that is not true. Option D is what? PA by VA is equal to PB by VB. That is also not true. Option B is given as PA is equal to PB and VA is not equal to VB. So this is right when you consider PA is equal to PB. Option C is given as PA is not equal to PB and VA is equal to VB. So here what happens, option B and C both seems to be correct. If they have specified any one condition again in the question, then it would be clear. But as according to the given question, only we can say that when the mass is equal, mu A and mu B are not equal in the container. So based on that, if any other condition is specified, we can mark it appropriately B or C. But as the pressure or volume, what it is equal, it is not specified. We can go for option B and option C both. Okay. Next question. Let A and B be the two gases. Let A and B be the two gases here. And it is given as Ta by Ma is equal to 4 into Tb by Mp, where T is the temperature and M is the molecular mass. If Ca and Cb are the RMS speed, then the ratio Ca by Cb will be equal to. So what they have given, that is one relation they have given, that is Ta by Ma is equal to 4 into Tb by Mb. Here T is the temperature, M is molecular mass. If Ca and Cb are the RMS speed, then the ratio of Ca by Cb will be. So RMS speed ratio they have asked here. Okay, we need to take the equation of Newton square speed equation that is given by VRMS is equal to under root of 3 into RT divided by M. 3 into RT divided by M. Therefore, we can write it as Ca divided by Cb is equal to Ca divided by Cb is equal to. So if I take in the ratio 3R will get cancelled. So we are left with what? Ta divided by Tb whole divided by Ma divided by Mb. Okay. So this is equal to root of 4. Why? Because in the question itself it is given. If you transfer that and if you write it as, it becomes Ta by Tb divided by Ma by Mb. That is equal to 4, it is remaining. So here it is under root of 4. So under root of 4 is nothing but what? Square root of 4 is, it is 2. Square root of 4 is nothing but it is 2. So what they have asked you? They have asked you the ratio of Ca by Cb, that is equal to 2 here. Therefore, the option A is the right option. Option A is the right option here, right? Next. The RMS speed of the molecules of a gas in a vessel is 400 meter per second. So RMS speed of the molecule is given in a vessel. It is 400 meter per second. if the half of the gas leaks out at a constant temperature, if half of the gas leaks out at a constant temperature, the RMS speed of the remaining molecule will be. So they have given that for a RMS speed of molecule is given as 400 meter per second, right? If the half of the gas leaks out at constant temperature, the RMS speed of the remaining molecules will be, that is, as we know that our root mean square velocity, it does not depend. It does not depend on the quantity of the gas. It does not depend on the quantity of the gas. Therefore, for a given gas and at constant temperature is always remains same. It always remains what? Same here. See what it is. I'll repeat. What the question is, what the RMS speed of the molecule of a gas in a vessel is 400. If the gas leaks out, means if the gas is coming out of that container, what happens to the RMS of remaining molecule? As we know that the RMS speed does not depend on the quantity of the gas. Okay. So if you see the equation for RMS, it does not depend on the quantity. Here at constant temperature, whatever may be the condition, it remains same only. It remains same only. It remains same in the sense option C, that is 400 meter per second. Next question. At what temperature is the root mean square velocity of gaseous hydrogen molecules is equal to that of oxygen molecule at 47 degree Celsius. See what it is given, that is the root mean square velocity of a gaseous hydrogen molecule is equal to that of oxygen molecule at 47 degree Celsius. So how we can do that? First we will take for oxygen. So for oxygen, the root mean square velocity is given by this for oxygen. It is under root of 3R PO2 divided by MO2. Then similarly for hydrogen also we can write is equal to under root of 3R PH2 divided by MH2. Then according to the problem, we can write it as under root of, they have specified that, what they have specified, these two are equal. These two are equal, which means that it can be written as 3RTO2 divided by MO2 is equal to under root of 3RTH2 divided by MH2 divided by MH2. So what happens here? Square root will get cancelled on both the sides. Then 3R will get cancelled on both the sides. Therefore, you are left with what? T of O2 divided by M of O2 is equal to H of T of H2 and M of H2. Correct? So, right. For oxygen molecule, the temperature is given as 47. Take it in terms of degree Celsius. It is given in terms of degree Celsius. Take it in terms of Kelvin divided by mass of oxygen is 32, which is equal to pH2. For hydrogen it is 2. Therefore, it becomes pH2 is equal to 320 divided by 32 into 2. So if you cancel and simplify this, 2 ones are 2 ones are 2 6s are. Then again, further if you simplify this, 16 ones are 16 twos are and 0. That is nothing but 20 Kelvin. That is nothing but 20 Kelvin. That is option A is the right option. Option A is the correct option, right? Cooking gas containers are kept in a lorry moving with uniform speed, which is moving with uniform speed. The temperature of the gas molecules inside will. See here, the cooking gas containers are kept in a lorry and it is moving with uniform speed. So when it is moving with uniform speed, what happens to the temperature? So here it increases, it decreases, it remains the same, decreases for some while increases for some. See, one thing we need to understand, if the temperature, if it is varying, what happens? So whatever the container is there, it will blast. So it is not that when it is moving, the temperature will increase, decrease, whatever may takes place, the it will be lost only. But so to avoid that, they will be taking all the safety measures. The temperature of the gas will be kept constant. According to common sense only, we can write it as it remains the same. But logically, how we can think this answer as option C is the right option. But logically, how we can say this is right? That is, if a lorry is moving with constant velocity, then what happens? VRMS value remains constant. So when VRMS remains constant, the temperature is, as the temperature is directly proportional to VRMS. When the VRMS is remaining constant, the temperature also remains constant. The temperature also remains constant here. That is option C is the right option. Next question. The molecules of a given mass of a gas have a RMS velocity of 200 meter per second at 27 degrees Celsius, and the pressure value is given. It is 1 into 10 raised to 5 Newton per meter square. When the temperature is 127 degrees Celsius and pressure is 0.5 into 10 raised to 5 Newton meter square, the RMS velocity in meter per second will be. So we need to calculate RMS velocity in meter per second. See, the RMS velocity is given for a molecule as 200 meter per second at 27 degrees Celsius, and pressure is 1 into 10 raised to 5 Newton per meter square. When temperature becomes 127 degrees Celsius and pressure becomes half, what happens to the RMS value? So let us see this one. In the previous question already we have discussed, as the temperature VRMS remains constant, the temperature value will vary. Sorry, the temperature will also remain constant. Here they have given the temperature is changing. So what happens to VRMS? We need to calculate that. See here. As we know that VRMS is directly proportional to square root of temperature. Let us take the ratio of temperature, that is V of 300 and V of 400. Means I have converted 200 and 127 in terms of Kelvin is equal to under root of, it is 300 divided by 400. So 0 0 will get cancelled. We will get it as root of 3 divided by 4. Right. So here V RMS of 400, it is sorry, this value is given. Okay, so this is given, it is given as how much? It is 200 divided by V 400 is equal to under root of 3 divided by 4. Therefore, here what happens? We can write it as V right? We can write it as root of 4 by 3 into 200. So root of 4 is nothing but 2. Therefore, we can write it as 2 into 200 divided by root 3. That is nothing but 2 into 2, that is 4. That is 400 divided by root 3 meter per second. This root 3 meter per, sorry, 400 divided by root 3 meter per second. That is option C is the right option. Okay. Next question. Which of the following statement is true? See what are the following statements they have given. Absolute 0 degree temperature is not zero energy temperature. Option B. Two different gases at same temperature pressure have equal root mean square velocity. But here option B is not correct. Why? Because pressure is not same. Pressure is not same. If it is given only for temperature, then this will be a correct answer. But pressure is not same here. Option C. The root mean square speed of a molecule of different ideal gases maintained at the same temperature are the same. It is for different ideal gases. So for different ideal gases, this condition is not satisfied. If it is for same gases, then it will be satisfied. Option D is what? Given sample of 1 cc of hydrogen and 1 cc of oxygen, both at NTP, oxygen sample has a large number of molecules. This is also not true. So option A is the right option. That is absolute temperature. The kinetic energy of the molecule becomes zero. They possesses potential energy. They possesses only potential energy. So we can say that absolute 0 degree temperature is not zero energy temperature. It is not zero energy temperature. Kinetic energy will be zero, but potential energy will be there. Therefore, option A is the right option here. Next question. 40 calories of heat is needed. 40 calories of heat is needed to raise the temperature of 1 mole of an ideal gas from 20 to 30 degrees Celsius. From 20 to 30 degrees Celsius at a constant pressure. The amount of heat required to raise its temperature over the same interval at a constant volume is. Here they have given the 40 calories of heat is needed to raise the temperature of 1 mole of an ideal monatomic gas. Okay. So number of moles is given, temperature is given, and pressure is specified as constant. The amount of heat required to raise its temperature over the same interval at a constant volume. So R is equal to, it is given as 2. See here, at constant pressure delta Q is equal to, it is mu Cp into delta T, mu Cp into delta T. So mu value is 1 because they have given it as 1 mole. Cp value they are saying it as constant. So it is Cv. Cv we should take. Okay. So this is 1 into R, that is 2 into 30 minus 20. This is equal to, so 30 minus 20 is how much? It is 10. 10 into 20, it is nothing but 20 calories. It is nothing but 20 calories. See here. So we can solve this question, that is 40 calorie of heat is needed to raise the temperature of 1 mole at constant pressure. So first let us calculate for constant pressure. What we will get for constant pressure, that is given by delta Q P is equal to, it is equal to mu into Cp into delta T. This is equal to mu value is 1, Cp I'll write as it is, and delta T is 30 minus 20. So 30 minus 20 is 10, that is, no, this value they have already given. This value, how much they have specified? They have specified it as 40, right? We know that Cp is equal to 4. Here, this becomes 10. So that is divided by 10. 40 by 10 is how much? It is 4, right? Therefore, Cp is equal to, we are getting it as 4. Cp is equal to, we are getting it as 4 here. Now we have Cv is equal to Cp minus R, which is equal to, Cp is 4, R value is given as 2. That is nothing but it is 2. That is nothing but it is 2 here. Okay, now in this equation, for QV is equal to, so mu value is 1, Cv value just now we calculated, it is 2, and here it is 30 minus 20. So if you simplify this, we will get it as 20 calories. We will get it as 20 calories. So first we need to calculate Cv value, then we can do this calculation. To calculate Cv, we have Cp minus R according to Mayer's relation. Then substitute the values and simplify. Two cylinders A and B fitted with pistons contain equal amount of an ideal diatomic gas at 300 Kelvin. So A and B fitted with a piston, it contains of equal ideal gas, diatomic gas at 300 Kelvin. The piston of A is free to move while that of B is held fixed. The same amount of heat is given to the gas in each cylinder. It is given in each cylinder. If the rise in temperature of the gas is in A is 30 Kelvin, then the rise in temperature of the gas in B is. So A and B is fitted with a equal amount of ideal diatomic gas at 300 Kelvin. Here the piston A is free to move while piston B is held fixed. Here what happens, that time the same amount of heat is given to the gas in each cylinder. So if the rise in temperature of the gas is gas in A is 30 Kelvin, then the rise in temperature of the gas in B is, so if B we need to calculate this one. See here, in both the cylinders A and B, the gases are diatomic. The gases are what? Diatomic. So for diatomic, the gamma value will be how much? It is 1.4. Right. So when the piston is free to move, it means that it is isobaric process. It is isobaric process. So piston B is fixed, which means that it is isochoric process. Right. So if the same amount of heat delta Q is given to both, then A is isobaric process and B is processing isochoric process. So that time here we can write it as delta Q of isobaric is equal to delta Q of isochoric process. Okay, so write the equation for delta Q. Here it is pressure is constant, therefore the equation becomes mu Cp into delta T is equal to mu Cv into delta P. So what we need to calculate, suppose if I take this is for A, this is for B. We need to calculate the temperature of the B. Therefore, simplify this equation for delta TB is equal to. So delta TB is equal to, it becomes, transfer the term, mu will get cancelled. So if mu will get cancelled, you are getting Cp divided by Cv. Cp divided by Cv into bracket delta T of A. So what is Cp by Cv is called as, the ratio of Cp by Cv is taken as what? Gamma. Gamma into delta T A, which is equal to, So what is the gamma value? Gamma value is taken as, it is 1.4 into, it is written as 1.4 into delta T A value, it is given as 30. So 30 into 1.4. So 30 into 1.4 is nothing but what it is? 42 Kelvin. It is 42 Kelvin. That is option, which is correct here. Option D is the right one. Okay, option D is the correct answer. Next. The temperature of 5 mole of a gas which was held at constant volume was changed from 100 degrees Celsius to 120 degrees Celsius. The change in internal energy was found to be, it was found to be 80 joules. They have specified the temperature of 5 mole of gas was held, the temperature was held constant. Okay, when the volume is changing from 100 to 120 degrees Celsius. The change in internal energy was found to be, the change in internal energy is given, it is 80 joules. The total heat capacity of the gas at constant volume will be. That is, at constant volume, the total energy is utilized to increase the temperature. So here we can write delta Q of V is equal to mu Cv into delta T. Okay, so this is equal to what we can write? That is mu Cv into bracket delta T. Change in temperature, it is nothing but what? It is 120 minus 100. It is 120 minus 100. So 120, and this value they have given it as 80 joules, right? Therefore, we will get it as mu Cv divided by is equal to 80 divided by 20. That is nothing but 4. So what we will get? We will get it as 4. So mu into CV is equal to, we are getting 4 joule per Kelvin. This is the heat capacity of what? 5 mole of gas. It is the heat capacity of 5 mole of gas. That is option C is the right option here. Option C is the right option. Okay. Next question. A gas is heated at constant pressure. The fraction of heat supplied used for external work is. So how we can do? Here they have given that a gas is heated at constant pressure. The fraction of the heat supplied used for external work is, which is used for external work is. See here. So we know that the fraction of energy which it goes to the internal energy. It goes to the internal energy, which is equal to 1 divided by gamma, which is equal to 1 divided by gamma. So we can say that the fraction of given energy that's supplied for external work is equal to. So here what happens when it is heated at constant pressure, the external work is given by, it is written as 1 minus 1 divided by gamma. 1 minus 1 divided by gamma, that is option B is the right option here. Okay. Next question. A monatomic gas expands at constant pressure on heating. The percentage of heat supplied that increases the internal energy of the gas and that is involved in the expansion is. See, they have given that monatomic gas expands at constant pressure on heating. The percentage of heat supplied that increases the internal energy of the gas and that is involved in the expansion, which is involved in the expansion. So how we can do this one? That is given by the fraction of energy supplied for the increase in the internal energy. It is given by what? It is 1 divided by gamma, which is equal to, for monatomic gas, it is written as 3 divided by 5. Okay. Gamma value is, it is 5 by 3. As here it is 1 by gamma, it is written as 3 divided by 5. The percentage energy is given by, the percentage energy is equal to, it is given by 30 by 5, that is nothing but 60%. That is nothing but 60% here. So for fraction of energy supplied, just now we have seen the formula, that is 1 divided by 1 minus gamma. The work that is equal to 1 minus 1 by gamma, which is equal to, it becomes gamma minus 1 divided by gamma is equal to, what is the gamma value? It is 5 by 3 minus 1 divided by, this gamma value is 5 by 3. So simplify this one. 5 by 3 minus 1 divided by 5 by 3. So in the numerator, we will get it as 2 by 3 divided by 5 by 3. 3 will get cancelled. Therefore, we will get it as what? 2 divided by 5. 2 divided by 5 here. So this is what 2 divided by 5 is the work done. What they have asked you, they have asked you, that is percentage. So percentage means how we will do, it is written as 2 by 5 into 100. It is written as 2 by 5 into 100. So 2 by 5 into 100 is nothing but what is 40%. It is 40%, right? Option which is correct here. The percentage energy is 60 and the work done percentage is 40, that is 64. Option C is the right option. Next, the density of a polyatomic gas is standard conditions is, so density of polyatomic gas molecule is given as 0.795 kg per meter. The specific heat of the gas at constant volume is, the specific heat at constant volume we need to calculate. See here the density of polyatomic is given. That is ideal gas equation for m gram of gas, it is given by this PV is equal to m into R T. So R is what? Specific gas constant here. Capital R is universal gas constant. Small r is specific gas constant. So this equation can be written as for P. P is equal to, it becomes m divided by V into R into T. So what is mass per unit volume is called as, it is density into R into T. Right? We want R is equal to, therefore specific gas constant R is equal to, it is P divided by rho into T. So P value, it is atmospheric pressure is 1.013 into 10 raised to 5 divided by density is given 0.795 into temperature, as it is given as standard, we can take it as 273. So this, if we simplify this, 1.013 into 10 raised to 5 divided by 0.795 into 10 to 73. So if I simplify this one, I'll get it as 466.7 is what? Specific gas constant value. They have asked you at constant volume. At constant volume in the sense, what we need to calculate? We need to go for CV calculation. So CV is equal to what we will get? CV is equal to, our formula is the specific gas constant R divided by gamma minus 1. This is equal to 466.7 divided by gamma, as it is a polyatomic, we can take it as 4 divided by 3 minus 1. It is 4 by 3 minus 1. So if I simplify this one, I'll get it as 1400 joules per kg per Kelvin. Joules per kg per Kelvin. That is option B is the right option here. Option B is the right option. Okay. So first, to calculate CV, we require R value. To calculate R, we can use ideal gas equation for specific gas constant. Okay. Next question. If 2 moles of diatomic gas and 1 mole of monatomic gas are mixed with, then the ratio of specific heat is, so here 2 mole of diatomic gas and 1 mole of monatomic gas is mixed. What happens to the specific heat? Let us calculate this. That is given by, calculation is little lengthy here. Here they have given that. So mu1, I'll take it as what? It is 1. So this is for what? Diatomic. Sorry, it is monoatomic. When mu1 is equal to 1, the gamma value, this is what? 5 divided by 3 for monoatomic. Then mu2 is equal to, it is 2 for diatomic. That time the gamma value will be, it is 7 by 5 for diatomic. Okay. So when they are mixed, the gamma of mixture is equal to, so our formula is gamma of mixture formula. So we need to remember this formula. It is given as mu1 gamma 1 divided by gamma 1 minus 1 plus mu2 gamma 2 divided by gamma 2 minus 1, this whole divided by mu 1 by gamma 1 minus 1 plus mu 2 divided by gamma 2 minus 1. So now we know all the values, we can substitute that. Mu 1 value is how much? It is 1 into gamma 1 value is 5 by 3 divided by gamma 1 value is, it is 5 by 3 minus 1 plus mu 2 value is 2 into gamma 2 value is 7 by 5. This is divided by gamma 2 value is 7 by 5 minus 1. This whole divided by mu 1 divided by mu 1, again it is 1 divided by gamma 1, it is 5 by 3 minus 1 plus mu 2 value is, it is 2 divided by gamma 2 value is 7 by 5 minus 1. So here the formula is very, very important. When two gases are mixed, we should know its mu value they have given in the question and gamma value. So gamma value for monatomic, diatomic, polyatomic, we need to remember the values here. Then the gamma of mixture is equal to, the simplification is a little complicated here, but one by one we can simplify. So first we can simplify this, that is 5 by 3 divided by 5 by 3 minus 1, it is nothing but 5, in the denominator we will get it as 2 by 3, so that is nothing but 5 will get cancelled, therefore we will get it as 5 by 2 plus, so here if you simplify you will get it as 7 divided by, then here the simplification is 3 by 2 plus it is 5. Then next, so simplify this one, you will get it as 19 divided by 13. It is 19 divided by 13. That is option C is the right option here. Option C is the right option. Okay, that is 19 divided by 13. So I'll repeat the formula. It is given as, when two gases are mixed, the gamma of mixture is given by mu 1 gamma 1 plus divided by gamma 1 minus 1 plus mu 2 gamma 2 divided by gamma 2 minus 1 whole divided by mu 1 divided by gamma 1 minus 1 plus mu 2 divided by gamma 2 minus 1, right? Next question. (22 gram of CO2 at 27 degrees Celsius is mixed with 16 gram of O2 at 37 degrees Celsius. So temperature and the mass is given, the temperature of mixture we need to calculate here. So heat gained by CO2 is equal to heat lost by O2. So here the principle of calorimetry we can use. Here what happens when the two gases are mixed, again the temperature, mixture temperature we need to calculate. Here heat lost by CO2 is equal to heat gained by CO2, because it is at 27 degrees Celsius and O2 is at 37 degrees Celsius. Therefore, heat gained by CO2 is equal to heat lost by O2. So here this equation is what? Mu1 CV1 delta T1 is equal to mu2 CV2 delta T2. Substitute all the values now. That is, it implies 22 divided by 44 into bracket 3R T minus 27 is equal to 16 divided by 32 into bracket 5 by 2 into R into bracket 37 minus T. So simplify this equation for T is equal to, we will get it as 32 degrees Celsius. So just transfer the terms, keep only T terms one side and remaining go everything on other side. Then we will get T is equal to 32 degree Celsius. That is option A is the right option here. Option A is the right option. One more question, last question for today's class, that is for a gas R by CV is equal to 0.67. This gas is made up of molecules which are, whether it is diatomic, mixture of di and poly, whether it is monoatomic or it is polyatomic. Let us see this one. How we can do this? That is by comparing with the relation of CV is equal to R divided by gamma minus 1. CV is equal to R divided by gamma minus 1. We will get it as simplify this for gamma minus 1 is equal to, it becomes R divided by CV. What is R divided by CV? R by CV is given, it is 0.67. Therefore, gamma is equal to, we will get it as 1 plus 0.67. That is nothing but 1.67. So when the gamma value is 1.67, it is nothing but it is monoatomic. It is monoatomic, right? That is option C is the right option here. Option C is the right option. Next question. At standard temperature and pressure, the density of a gas is, they have given the density of the gas, that is 1.3 gram per meter cube. Next, the speed of the sound in gas is 330 meter per second. They have asked you to calculate the degree of freedom. So how to calculate the degree of freedom? Let us see. See here, that is velocity, they have given it as how much it is? Velocity is given as 330 meter per second, right? So mean free path value is given, that is lambda is equal to 0.8 into 10 raised to minus 7 meter. Okay, then the number of molecules per unit volume is given, that is N is equal to, it is 2.7 into 10 to the power of 25. Okay, so substituting the value in the mean free path equation, that is lambda is equal to 1 divided by root 2 into pi n d square. So substitute the value here. We need to calculate diameter of the molecule. Therefore, diameter d is equal to under root of 1.04 into 10 raised to minus 19. So if you substitute all the values and simplify this, diameter d is equal to, we will get it as 3.2 angstrom. 3.2 angstrom. That is option B is the right option here. Okay. So this completes the kinetic theory of gases. In the next class, let us discuss the next topic. Thank you.